So, hey everybody, I'd love to introduce Jeff Caers from Stanford University and the Mineral X project, where I guess to summarize, you want to make sure that uh, geology and minerals are available to all. Welcome.
Thank you, Craig, and glad to be here. So in my presentation, I'll talk more generally about intelligent agents and how such technology can be used to accelerate the energy transition, and then specifically talk about our new program, Mineral X. Okay, wrong slide. Of course, I'd like to start by acknowledging my collaborators. We have a growing group on Mineral X, and we're also collaborating with the Stanford Intelligent Systems Lab that is led by Michael Kochendorfer, a professor in aeronautics and astronautics. Also mentioned a lot of collaboration with OMV, which is an energy company in Austria, and also with Cobalt Metals, which is a startup in the space of mineral exploration. So yeah, let's talk about energy and energy transition. And there's many people now thinking about, well, let's go to 100% renewable energy, and I'll mention that in a little bit. And so in doing so, I was also thinking about what would be the essential ingredients to achieve this transition. And if you look at that, the answer would be four major categories: wind and solar, water for hydropower, the Earth's heat, geothermal, both for shallow as well as deep geothermal, and then Earth materials or Earth's minerals. And so of all of these components, it is the last component here, Earth's minerals, that is probably the most critical in terms of getting the right supply or getting the supply for those Earth's minerals. So let's talk a little bit about these various components. One that's often not looked at is that of geothermal, shallow geothermal or low enthalpy geothermal for heating and cooling. And as you know, with climate change and the increase in droughts and extreme temperatures, it was actually a piece in the Wall Street Journal, I think, a couple of days ago, about how China is increasing coal burning because of the high temperatures, and so cooling is a big issue. Now in China, most cooling and heating is done. There's no distributed gas, so there's mostly done through electricity, and so electricity is generated by coal. And so in large areas such as the Yangtze River Delta, which hosts 235 million people, we're collaborating there to look into transitioning into geothermal heating. More closer to a smaller area in the world that we're actually collaborating already in terms of engineering projects is in Vienna. Vienna sits in a basin. It's actually an oil and gas basin, and in the basin there are some shallower heat sources. Now this is not as shallow as we would have for heat pumps. This is probably a few thousand. This is actually a few thousand feet below the surface. And so what we try to do there is to circulate water into the subsurface, use the subsurface as a heat exchanger, and then use that for district heating. And so these are large projects, engineering projects. These are projects that tap into the subsurface. Here we see that kind of layer, so to speak, in Vienna, below Vienna, where you see temperatures reaching to about shallower to about 80 to 90 degrees centigrade. Now that's good enough for heating. It's not good enough for energy production. So for energy production, you need to go much deeper, and you need to go to about 150 degrees centigrade. Now, geothermal heating requires injecting fluids in the subsurface, and that is in order to engineer that, you have to build subsurface models in 3D, and there's an example shown here. But also what is shown in this example is that there are faults. Here you see these stripes here. These are faults in the subsurface. So injecting fluids into faults or near faults is not desirable for this reason here. This was an earthquake recorded in Pohang, South Korea, a magnitude 5.4, which is significant, as you see. And this is due to geothermal energy production. And the reason here, as explained on the right-hand side, is that as you inject fluids in the subsurface, you change pressures. Once you change pressures on faults, you may get slip, and slip causes earthquakes. And so knowing that this is going to happen and how is this going to happen is, of course, very important, and a very important design of the safety issues related to geothermal energy production as well as shallow geothermal. It's one of the critical issues for geothermal because you can imagine if there's even a small earthquake in Vienna, that will be the end of geothermal energy in Vienna, and that is something that's not desirable. Another major component of the energy transition is that of industrial heat. There are many alternatives there, such as electrical furnaces. And one of the alternatives that people are promoting is that of combining combustion with underground storage. So this capture and storage, also known as CCS or CCUS, and putting it underground is called geological storage or GCS. So that requires capturing the CO2, which needs which requires amine plants, and then storing it underground in a supercritical form. So there you have a double jeopardy if you start doing that, and that is to do with leakage. So the safety issue there is related to injecting fluids in the subsurface that may leak over time through faults into probably groundwater systems. And so this is more of a waste storage issue, which you could say is somewhat similar to nuclear waste storage, is that you need to guarantee that this leakage has very low probability over very long time periods. And so that is also a critical aspect of this design aspect. Okay, so then we talk about also the minerals and the circular materials economy, where we are replacing ICE vehicles with electrical vehicles, and sure you've seen many articles about that in the newspaper, and there are a number of critical elements that are appearing here. I would say the most critical of these is lithium today, because lithium is the dominating element in lithium-ion batteries, and lithium-ion batteries are going to be around for now a significant amount of time, but people say at least 1 decade, if not more. In order to build motors and build electrification, you need copper. So I'd say copper is the second critical element here. A good alternative to cobalt is nickel. You know that some electrical vehicles use use batteries that contain nickel. There's also iron-based batteries. They don't have nickel, but they are less performing. So nickel and cobalt have to do a lot with the performance of electrical vehicles. Now, that's where our new group comes in, the Mineral X. I'll talk a little bit about that at the end, where we collaborate with Cobalt Metals to increase the discovery of these critical elements. Now, this is quite challenging, and as you see here, the top graph is sort of the decline over the last couple of decades in the ratio of success for mineral exploration. And so this decline is tenfold. In fact, in the last 2 decades, there are no major new copper mine has been discovered, and people continue mining increasingly low-grade deposits, which is very harmful for the environment. So talk later a little bit about how we try to find minerals and how do we use artificial intelligence to do so. So in that sense, for critical minerals, there are a number of very sobering facts. Is that number one is that the United States is absolutely not ready to secure its own critical mineral supply. A lot has to do with the fact that to go from a discovery to a mine takes at least 10 years in the United States, and so that's not fast enough. Secondly, there is almost no attention paid over the last 2 decades on critical minerals. Lots of the effort in energy in the United States has been on fossil fuels, and so we're very, very far behind many other countries. As I mentioned, this critical mineral discovery efficiency has been declining, and so that's a major concern. And so therefore, you can almost say that this resilient, decarbonized, and just critical mineral supply remains very uncertain. By just, I mean essentially that there's an environmental justice concern that we should not be getting these minerals out of poor countries and then drive very expensive vehicles in the West. So this whole issue around the resources curse remains very important, and that's something that our group wants to contribute to as well. In terms of recycling, I get that question a lot. Recycling is not going to be important in the short term, simply because of the second and third life of lithium-ion batteries. For example, lithium-ion batteries have a second life as a storage battery. And so that means that any serious recycling is only going to kick in by 2035 or later. So then the question we can ask ourselves, okay, what is now really needed to make this energy transition a success? And what are plans that are available, and how can we execute these plans? Now, there are many plans, of course, available that have been promoted by the IPCC or the International Energy Agency or even fossil fuel companies. And so I'm looking at two plans, however, that are very different. And I'm a big believer in these two plans. These two plans actually look very similar. The one is by Mark Jacobson, who is a professor here at the Dorr School of Sustainability. And he says that we have all the technology mostly there. Lithium-ion batteries, let's say geothermal heat pumps, wind and solar, hydropower, lots of this, green hydrogen, lots of this is already there. And so the technology of today can be used. So that's good news, right? We don't need any, at least according to him, and I agree with that, we don't need miracle technologies. On the other side, you see Tesla's master plan, which came out in April this year, which looks very similar. And that master plan also doesn't call for any fossil fuels, doesn't call for those things. And also it calls a little bit more for nuclear, that Mark Jacobson is not very in favor. So you can ask ourselves, okay, what is then really needed if everything is there? And so my take on that is that we need to scale this, accelerate this, we need to build infrastructure, we need to source the material, optimize system, and of course create the right policies for investment. And so these are what I call intelligence decisions. And so then the question is, how can we make such complex intelligent decisions? So my take on that is that making complex decisions over long time horizons require artificial intelligence. And humans, because simply humans aren't good at making very long, number one, deciding or judging, making judgments under uncertainty over very long time horizons. And that's been very well documented. It's not just my opinion. It's been very well documented by two Nobel Prize winners in economy, Tversky and Kahneman. They talked about judgment under uncertainty and how people are very biased in the way they reason about the future and about data. And so that comes into the heart of artificial intelligence. So when I talk about artificial intelligence, I want to make clear that that we agree on the this categorization here, which is the AI. That's big buzz right now is of course the predictive and generative AI, and so that has an important role into what I do. But the most important role is the decision-making AI. ChatGPT doesn't make decisions, so we need to build agents that can make intelligent decisions and reason, act, and adapt in a real environment. So more talking about kind of robotic type AI or chess playing AI or game AI. That's the AI I would be mostly talking about. So let's now go and check how, as I mentioned in the abstract, how we have essentially implemented some of this AI into these energy transition.
Question.
Yeah.
As you go through this, it seems like a major challenge, again, before AI is understanding how supply chains work. Which ports are available to get minerals from, let's say, Australia to Argentina.
Yeah.
Some details are, they can multiply. So how do you account for all the complications of real economies?
Yeah, I'll talk about that at the end. Very good question.
Awesome.
Yeah, absolutely. Talk about that at the end. Okay, so how can AI accelerate this transition to renewable, or help accelerate this transition? So the first thing to think about that is that planning in exploration engineering, and then later on I'll talk about mineral supply chains, that humans are slow and have limited time horizon, right? And so artificial intelligence is really great at long time horizon planning, and including reasoning with uncertainty. And uncertainty is key to all of this, and we'll talk about that in a bit. I like to use this analogy. Every time I wake up in the morning and I just reached my 100 day streak at the Wordle game. We play Wordle. We can play Wordle with 5 letters, relatively smart. And there's an AI, as you know, behind this as well. You can compare yourself with. But think about playing this game in German, which, as you know, the word for computer in German is Datenverarbeitungsmaschinen. And so imagine playing that word, and that only the probability of the letters is revealed to you. So not even whether the letter is there or yes or not with certainty. So that is the kind of problems I'm trying to solve. So these problems, like CO2 injection or planning of mineral supply chains, long-term planning, are essentially what we call sequential planning on uncertainty problems. And so these are problems where we need to make decisions today over actions that are going to take place in time in the future. And when it comes down to subsurface operations, we typically would look into actions of injecting, but then also action of monitoring. And that monitoring is required because of the safety issues that I mentioned. So the monitoring could then monitor the fluids in the subsurface as they accumulate. But of course, this is not known with certainty. Actually, there's quite a lot of uncertainty around that because we do not know perfectly the subsurface structures that are there or porosity within which these fluids are going to be contained. So the question, therefore, is how do we choose sites to inject? And so in one site, you may have different injection wells. And what kind of monitoring do we do? And so there's many choices. You can have very expensive, accurate monitoring, but that's often not something that's feasible over the long time. And then you have more inaccurate monitoring that is more extensive. So you're trading off precision versus accuracy here. So here's a sort of a mock-up example where we're going to inject into the subsurface here into the system, and there are faults on the side. And so you don't want to reach these faults because then you get leakage to the subsurface. Now, here you see what the AI does. Number one, I'd like you to focus on these gray curves. This is the uncertainty on the top surface. So this is realistic uncertainty because we do not measure exactly the position of these surfaces because the geophysical measurements are limited in doing so. So the agent decides here to inject into this black location at a certain rate. So this is all decided. And at the same time, it decides to monitor here with these blue arrows are the locations where you're going to be monitoring. And monitoring will reveal more about where the fluid is, and will also reveal more about uncertainty on these surfaces. So you see, this is not a trivial solution. And it is also a solution that needs to include the time element. So you could say, well, this seems like an optimization problem. Well, it's more difficult than an optimization problem. It's a sequential optimization problem that happens over time. What that means is that to the present decision, where you inject today and where you're going to plan monitoring today, will need to take into account that in the future you will get information. So you see that there's a feedback loop of information in the future to optimize the decision today, and that is not a trivial exercise. This is not a simple optimization problem. And so the reward is here on the right hand side is that you want to maximize the trapped volume and of course minimize or even set to zero the exited volume. So with this example, we can start thinking about Yeah.
So are you, I mean, this looks a lot like a Gaussian process, like in this illustration, but is
It,
that
it
your
is.
approach?
Yeah. Mhm.
So it's more like that. And do you use like more hardcore simulations that are more expensive, but harder to, more expensive to work with?
Yeah, so that's a good question. So number one, I'd say that the
Right.
geological uncertainty is a whole lot more complex than that's very simple, and I'll come
Right.
back to that, right? So that's number one. That's a hard problem. I'll talk about that. The second is indeed that in the real cases, which I'll show you in the next, we're dealing with physical simulators that are very slow because when you're injecting CO2, you get miscible flow, and so this is needs a very high resolution to get that resolved. And so we're also looking with proxy models, and I'll talk about that as well.
Okay, and then like if you do simulation, should I be thinking that you have one measurement and you say, well, here's the possible ways it might work out, then put another measurement on there. Here's like a game kind of.
Yeah, I'll show. Yeah, exactly. I'll show how that game is played
Got it.
in the next slides. Yeah. So I'd like to think about, therefore, not so about the algorithms, because I think it's very important to think about the formulation of this problem. So the formulation of this problem, and then think about the algorithms that solve this formulation. So there, if you think about this problem, there are four major components that are distinct. Number one is that we have to get to a certain reward at the end, which has many components. Some of these may be conflicting. There are actions that are taking place in the real world. So drilling is an action, injecting is an action, and then there are observations. Then you have uncertainty, right, on one hand side. So uncertainty is a very complex issue, and I'll come back to that. It's not a simple uncertainty because we're dealing with the 3D Earth, which consists of faults and layers and porosity and permeability and rocks and fluids and all kind of stuff and chemistry, and so lots of complexity there. But then also we have observations that can help us reduce that uncertainty. Now, we only want to reduce uncertainty to the point that it actually affects the choice of the actions, and that is based on the reward. So this is all interconnected, and the interconnection is this one, which is this dynamic decision network that says that if you're going to take an action at some time t-1, that's going to lead to an observation, and then the next action you take is going to lead to a reward, but that reward is uncertain. So that means that there's uncertainty in that reward, and so we have to account for that uncertainty. And that observations are going to help us in reducing that uncertainty. And so in AI, uncertainty is also called belief. And so this is that decision diagram that with the next action, with the current action, the current observation, you can then update the belief into a new belief. And so this plays over time. And then at the end, you get the final reward. And the final reward needs then to be discounted to the present. And then you need to solve this problem, right? To solve this, what combination of actions would you take in the future in order to maximize the reward? And so the outcome of this is a policy, which is the prescribed actions given the states that you're in order to maximize a reward. And so this is very similar to playing chess. Except that in chess you observe pretty much everything accurately. Actually, you do. So the way that it's solved, and this is what you were talking about earlier, is that we need to start with trying to find those actions, observation combinations that lead us to an optimal reward. Now, the problem is that as you go over time and you start with a certain observation that leads to an action, which then itself leads to more observations, which leads to also possible actions. You see that this is exponentially exploding, in particular because in my problems that I work with, everything is pretty much infinite dimensional. The Earth has billions of parameters. You can put the location of the wells in a large amount of possibilities. You can inject with large amount of possibilities of rates and whatnot. So this is kind of shows here on the right hand side is this visualization of this observation action pairs. And so the way that is solved is with typically Monte Carlo tree search solvers. So this is a family of algorithms that it looks to exploit those action observation pairs that lead to very high expected reward. And so that itself is a whole field of computer science and AI that I collaborate with Michael Kochendorfer in order to do that. So if you look at that, so we submitted this paper to Nature, I think in June, and what was critical about the outcome of this is if you, number one, if you assume no uncertainty, you will get leakage. If you assume that you're optimizing under uncertainty using, let's say, closed loop optimization, you don't use. But the problem there is that you're predicting you don't have leakage, but in reality, you do get leakage. It's only when you formulate the problem as this partially observable Markov decision problem, which is the graph I showed in the previous slide, and when you start using proper uncertainty quantification methods, here sequential important resampling with rigorous Monte Carlo tree search, it's only in those circumstances that we find there is no leakage. So that also shows that this interaction between data in the future and the current operations is actually quite important. So now we go and apply that to with OMV, which is that Austrian oil company, and do that in actual field work. Can't tell you much about this because there's a lot of sensitivity around injecting CO2 in the subsurface still. You know, there's license to operate in the areas within this with this case lies, and this case is a depleted gas reservoir. So these are gas reservoirs that contain natural gas. They have now been depleted. Went from 100 bar to 10 bar, and so now you can re-inject the CO2 in there. So this is one of the great opportunities for CO2 injection, but it's not without risk. And the reason for that is that subsurface contained faults. The reservoir has been depleted, so now you're like a balloon, right? And now you blow it up again. So what's going to happen to the rocks? Are they going to what are the geomechanical properties, and what are stresses and strains that are going to happen as you start injecting? So monitoring is very important, and where to place monitoring wells. In this case, we have 18 wells in this old gas reservoir, so we can use existing wells to monitor, and then we can use existing wells to inject. And so now come back to your issue of the forward modeling. So in order to make predictions of reward, we need to build subsurface models. And there's uncertainty in the structure, and there's uncertainty in the rocks that we have to account for. And then we forward simulate that. But that forward simulation takes a lot of time. And so when you're doing an AI solver, you may need hundreds of thousands of forward models. And so using actual physical simulator doesn't work. And so that's where we use deep learning techniques in order to predict or replace that forward model. And that's actually not as trivial, because the forward model is not just function of the physics of the problem, it's also a function of the location of the wells. And so the location of the wells is something you need to search over. So you need a forward model that's not just replicating the physics, it's also replicating the physics over a whole set of possible future boundary conditions. And so that's quite an important work. And so that's where one of our students that we collaborated with has done quite an interesting contribution.
So question.
Yeah.
You say you do 100,000, hundreds of thousands of runs per one of these studies. How many do you need to train one of these surrogates?
8,000.
8,000, okay.
Yeah.
That's much better, at least.
That's much better, yeah. And the accuracy of the surrogacy is actually quite important. So we trained first with 2,000 and it didn't work because the surrogate model wasn't accurate enough. And because of the sensitivity to the leakage, and leakage being a low probability event, you know, you actually have to have quite accurate surrogates in order for this to work.
Okay, and then the other thing is you presumably have to bound the space of possible geologies and boundary conditions pretty well. You want to, do you like just randomly sample different kinds of geologies? Do you have a curated set? Is it adaptive? You generate geologies where you seem to have been getting errors? Yeah,
so we just submitted a paper on importance sampling for creating cases. If you do random sampling, you're going to create a whole bunch of cases you don't need to have. So we employ importance sampling that creates cases that are interesting cases that in cases where you have leakage, you need to predict it very accurately. In cases where you don't have leakage, it's just you don't really worry about those cases. So important sampling can actually reduce the amount of simulations you need by tenfold relative to naive Monte Carlo sampling. So there's a lot of work there done as well.
And are generative models useful here to generate, useful subsurface geologies?
Not in this is generating the So we do work on generative models for subsurface, but not in this case because this case the generation of the models is very fast. So generative models could come in, for example, in solving inverse problems, right? Because if the inverse simulators are slow too. But here we use particle filters and sequential importance resampling. So again, we're combining importance sampling with particle filters in order to produce particle sets that solves the inverse problem very fast. Because solving the inverse problem itself is difficult because you're observing a concentration and at a certain location, and you need to back out the surface topography, the saturation, as well as the porosity of the system. So these inverse problems themselves are quite challenging.
That makes sense. What I was thinking generative was if you need to do important sampling, and I would think unless you have a library of many geologies, which actually you may, you need to generate a bunch of geologies. Now, I'm not sure how difficult this is.
This is easy.
Okay.
This is super easy. Yeah, this is super easy.
So it's like a matter of saying, here's some layers, here's a crack, and you're done.
Yeah, I mean, we in this case those are they're constrained by geophysical data, but then in order to simulate the high resolution component, we use Gaussian processes in this particular case.
Okay, that makes sense. Thank you.
There are cases where you need to model complicated geometries of stratigraphy layering or fishes, means rocks, and so there often people use more of the generative approach.
Okay, yeah, I see the difference. You usually have fairly stable kind of formations, and so yeah.
In this setting, yeah. Okay, so here you got then the answer, which is the 3 locations where to inject and the 1 location in order to monitor. And so this is not intuitive at all, right? So you see that it injects in 3 different periods, and then why would you put this monitoring well there? And so that is what this AI can decide, and so this is being implemented now for this specific site. Okay, so we talked about Earth's heat. Let's now talk about Earth's materials. And so now the whole idea is to keep the exact same formulation. This is the power, I think, of all of this, is we're not changing formulation, because the formulation is that of sequential planning under uncertainty. So now, instead of doing safety and subsurface injection, when you go to Earth's minerals and say you would like to discover materials then that eventually need to be mined, that is also a sequence of actions. In fact, we'll talk a little bit more about mineral exploration, why that is a sequence of actions that is taking place in time, but also mining and then eventually supply chains are also a set of sequence of actions that need to be done in time in order to build them. So a little bit about mineral deposits, because this may not be so well known. So mineral deposits and metal deposits in particular, there are many different kinds. The kind that we are looking for are high-grade deposits, and the reason we're looking for those is that they, and I'll show an example of that in a bit, is that their environmental footprint of mining is so much smaller than a low-grade deposit. You can imagine that if you're mining a nickel laterite deposit in Indonesia, which has 0.2% nickel, that means that 99.8% of what you mine is waste. And so the question is, where does the waste go? So you're basically clearing out the rainforest, number one, the topsoil, and then you're putting the topsoil back. And so you can imagine the environmental destruction that go with that. We're looking for, in my group, we're looking for these hard rock massive sulfides, which contain nickel, copper, cobalt. And these things are below the ground, which just makes them hard to find, but they are very small in super high concentrations of nickel percent, 3-4% nickel. As you see, that's better than 0.3% nickel. And so this can be mined underground. So these deposits are formed through intrusions, and these intrusions, they bring magmatic fluids to the surface through areas where the crust is thinning, and think about mid-continental rift areas where then these fluids interact with sulfur in the continental crust, and then deposit in chambers, either in intrusions or even lava tubes, and then they settle to the bottom because these are very heavy things, and so sometimes they concentrate in significant form to form an ore deposit. Now, finding that it requires a lot of effort, and you can imagine it almost starts from space. Here we have the mid-continental rift system, which is the border between Canada and the United States, which you can see from space, and you can actually see the rifting. But then you're looking for something here on the right-hand side that is at a much smaller scale, which is the intrusion. So there's a top view of the intrusion. And then you go to the area where you want to do more prospecting, and then you need to put loops underground where you can do geophysics. But eventually you have to start drilling, and that's where the expense comes, because drilling requires a lot of equipment. It requires permitting, and sometimes you can't access the area well. These are in very remote area. For example, we're exploring in the Arctic, above the Arctic Circle, where there's absolutely no roads whatsoever, and you bring in planes to do the drilling. So you can imagine this is expensive. It takes a lot of time.
So a question.
Yeah.
When you say intrusion, it sounds like you mean, because it's an aerial feature, which is surprising to me. It sounds like it's just one of those processes like a lava tube that creates a void underground that makes it even plausible for minerals to accumulate. Is that right?
Exactly the case. So that doesn't mean there are minerals there. It means that there's a possibility of minerals. There's many of these intrusions that contain absolutely no minerals.
So you're looking for surface signs of underground voids.
That's one, yeah. For these massive sulfides, we're looking for indeed what are called voids that are filled with mafic rocks. So rocks that have high iron magnesium content, or ultra mafic rocks, very high.
And then you have a place for the minerals to drip over millions of years.
Yeah, yeah, exactly. Yeah.
Got it.
This one happened 1.3 billion years ago.
Okay.
Yeah, that's not recent.
Right.
So the problem, as I mentioned, is in the subsurface. So a lot of these surface expressing deposits have been found. So now we're looking for things that are in the subsurface. So it means, you have a layer of sediment. You can stand on a piece of dirt and say, well, below our feet could be something. And so geophysical measurements come in as very important. But of course, a lot of things look like an ore body. And so the way we try to discover ore bodies is looking for specific geophysical signatures. This high conductivity, magnetic susceptibility, and all of these things. But a lot of things look like that. Graphite looks, it's very conductive. So many companies have drilled into graphite. And so you have what is called high false positive rates. And so what we work a lot on is how can you really start rethinking the idea of mineral exploration. And so I've come up with the idea of what's called Bayesian mineral exploration, because I found that mining companies or exploration companies tend to want to confirm their expectations of where the mineral deposit is. And confirming expectations when you have a rare event leads to extremely high false positive rates. That's been basically one of Popper's contribution, saying that in order to predict something very rare, you need evidence that is trying to falsify your hypothesis. So as you were mentioning in the previous slide, it's not just about confirming the presence, it's also making geological hypotheses about the voids and the system of where the mineral system of how that was created, and then try to find falsifying evidence. And most companies don't do that. Most companies try to find confirming evidence. And so with cobalt metals, we've gone the completely opposite way and say we need to first falsify hypotheses and then try to confirm them. And so that's kind of a revolution in this world that is called Bayesian mineral exploration. So we are using Bayes' rule and we're using Bayesianism, but one of the key points in all of this is the the model is really driven not by a 3D model, but it's really driven by geological hypothesis. Is that we really don't understand very well the formation of these mineral deposits, and therefore we really don't understand well the geometries within which these end up being, and why, for example, one intrusion has absolutely nothing and another intrusion has, you know, a lot of minerals. So we don't really understand that. So we need to formulate hypotheses and try to find evidence to falsify them before confirming them. So that means it's all about the sequence of future information gathering. So now it's not just about let's do the next thing, drill. It's also about can we plan in the future. So this is sequential planning under uncertainty. So now we go back to our original formulation. And that's where we have built something completely new in the mineral resources industry, and it's called the Intelligent Prospector. So it is the same formulation as the CO2 or the geothermal case. It's a program that makes decisions, you know, that are planned over time, where the current decision is going to take into account the fact that you're going to make many more actions in the future, and we'll get information in the future, right? It's blind. It's like playing chess. You don't play chess one move at a time. You don't do chess by closed loop optimization. You need to do this in this Markov decision process form. Now, to do that, you need a huge amount of information. And so with Cobalt, you know, we've worked a lot on ingesting tens of thousands of even handwritten documents that go back to the Belgian Congo time in Africa to look at hand-painted maps and things like that. Because a lot of these areas, there's absolutely no information, at least if you go look online in databases. And so ingesting that information and doing that in a rigorous way is itself, using NLP, is a significant undertaking. But once you have that, you can start act on that information. And that is where, you know, I think with Cobalt, we have made a huge difference. And this was a big announcement that came in the US Africa Summit that was held just last year, where Cobalt was mentioned, or is the company went into a deal with an investor in Zambia. And the reason why Cobalt got this deal, which was $150 million investment in the copper belt in Zambia. So this is an area of the world where you have a huge amount of copper and cobalt. Cobalt comes from the north, which is the DRC, as you know, and all the problems. And Zambia is a democratic country with a very different regime, and is in the south and has mostly copper. So the deal was made because Cobalt has proven that they can accelerate the development of resources and the development of exploration orders of magnitude faster than regular mining companies do today. And I'll show you what that is exactly. So here's a drill bit, a drill well that is drilled currently ongoing in Zambia by Cobalt. So you see, you know, this is real life stuff. And this is one of the first wells or drill holes that were drilled using artificial intelligence to determine the location and the angle of intersection. So what's going on? So imagine that you here on the left-hand side, you are in Zambia, somewhere in the copper belt, and all the little dots you see here are the way that mining companies today do exploration. So literally thousands and thousands of wells or drill holes are being drilled in order to make assessment of whether or not you have an economic deposit that you can start developing. So what we do with Cobalt is we don't do it that way at all. And I'm going to show you kind of a mock-up case of what is happening in Zambia, because of course of the sensitivity of the issue, I can't really talk about the details. But here's what's happening. So you see that we don't drill on a grid and then wait for the results. We drill one at a time, but our reward is essentially trying to making sure that the uncertainty on your risk, which is determined by some economic cutoff, which you see here, this red line on the right-hand side, is sufficient for you to make a decision to go ahead or walk away with the mine. That is really the setting that we're looking into. And you see uncertainty is a key part, because if you see initially there's lots of uncertainty and it looks like, you know, you're sort of on the right-hand side of the cutoff. But as you start building out the sequence of drilling, you end up on the left-hand side of the cutoff. And so you can see that the sequence of drilling is not intuitive. at all, but it is very intuitive to the intelligent agent because it takes into account the fact that future information will help you improve on your current decision. And so in doing that, you end up with an order of magnitude here, less drilling, which is just an enormous, number one, cost reduction, and secondly, also time, right? This can be done maybe in 9 months instead of 3 years. And so that's also a big advantage.
So question. So this, I mean, I'm trying to say, I mean this very positively. This sounds obvious, and this is like exactly how it should be done.
Yeah.
But I'm also thinking that the subsurface geology field has had some Bayesian approaches like kriging for like a good century. So what was the gap that prevented them from using techniques like this until now?
Well, I think the gap was that people were the industry is, and it is not a scientific problem. It is the industry is holding on to very conservative ways of doing, and so this is just a huge inertia. While you are of a more modern education, these people don't even know about AI or don't even know what machine learning is. The first time I met with major mining companies in their exploration team, they did not know what machine learning was and what it would do. Most of the drilling was just basically gut feeling by a geologist or an expert, and so this moves this forward. Now, a mining company. The problem with the mining companies is that they don't have this vertical integration of data science, AI, geology, geophysics, which Cobalt Metals has, right? So there's a company now of more than 100 people working on 50 assets in 3 continents, where there are teams of people that are expert in this particular thing, and also expert, the world's best geologist. You just don't find that in a mining company. It's just not there. So it's not Google, right? So they don't have that that expertise whatsoever.
Okay, so then, to what extent were they using simulations and
nothing at all? Nothing.
That one surprises me, because that is a very established, like, just inverse model of what must be underground from your set wells.
Yeah, well, yeah, but it's deterministic inverse modeling.
Right. So I guess what you're saying is that the big breakthrough is the running it many times, adaptive decision making. That's the new thing.
So the new thing is uncertainty.
Okay.
Uncertainty quantification. That's the new thing. So they don't do uncertainty quantification, period.
And without that, you can't have Bayesian.
And without that, you can have Bayes, or you can't do anything AI. And so to get them in the uncertainty world, because everyone's doing, basically what is done is you do a deterministic geophysical inversion, you see an anomaly, and you drill in the middle of the anomaly, and you find nothing, and you walk to the next one, and you do that 100 times.
Okay. And that's adaptive, but without uncertainty, it's kind of dumb.
Not adaptive because you don't learn anything. It's not adaptive.
You just find nothing there.
There's nothing there. No. There's nothing there. Yeah, I'm sorry.
Yeah, that makes sense.
Yeah.
To what extent is the cost of these simulations the bottleneck for uncertainty qualification, and what is it? Just the algorithms.
No, and that's where you have to leverage high performance computing, right? And that's what we do here to run these, solve these monocorollate research methods. You need HPC. There's no way around that. So we use cloud computing, right? Say Cobalt use Amazon Web Services and stuff like that, and Google Web Services or whatnot, right? So they use those services to do that, but a mining company doesn't do that.
Right, and then when you also have surrogates, those searches become much more tractable or much larger because they're cheaper. Okay.
Yeah.
Got it. Thank you.
Now, all companies are much better at this.
That must be what I was thinking of, because I think I've heard more of them using
non-mining companies. Non-mining.
No. Okay.
No. Okay, so then you can say, and I come back to what else uncertainty planning is there? Well, all long-term horizon planning and energy system planning are planners under uncertainty, and so now we are going and scaling this up to all complete new applications. And I'll come back to the question was asked earlier about the ports in Argentina and Australia, and where's the minerals going to come from. So we are starting a very large project around intelligent design of lithium supply chain. So now we're looking at the supply all the way from exploration to recycling. and building that up. And this is, of course, a significant project, right? You start to see that. Now, we started lithium because lithium, number one, is the most important one. And secondly, lithium comes mostly from our allies. So 95% of all lithium for the United States, electrical vehicles and other applications come from Australia and South America. And so we are, the Biden administration made a pact with Australian government only 2 months ago around considering the Australian as a US domestic supply. Now, there's lots of problems with that because right now the Chinese are heavily invested in Australia. And so there's a question now of how can we, mitigate this issue of the Chinese dominating, not so much the mining, but dominating the processing, because most of the ore processing, the ore gets shipped to China from Australia, gets processed there, the spodumene, and then gets shipped back to Australia. So you can see the domination of the Chinese in this area, right? And so what we like to do is to come up with economically viable, using material flow analysis and system dynamics to build up these supply chains such that, as you see on the right-hand side, they meet certain criteria, which we call rewards. Which, decarbonization, very important, resilience, important, social license to operate. So there's going to be social models involved. And the idea is to say, how can we delay mining in the United States as long as possible? And the reason why we do that is because there is no license to operate in the United States for mining. Even if you say, I find a deposit, I want to mine tomorrow, people just don't want it in their backyard. And so there has to be first this whole ramp up in the United States for, I think, at least 10 years before we can start doing any significant mining, and delay that as long as possible. But at the same time, leverage Australia, particularly Australia. Why Australia? Because Australia has all of the hard rock lithium, which is different from the brine lithium in South America. The hard rock lithium is the future for lithium, simply because we know all the brine deposits, and at some point they're going to decline. And the hard rock lithium is the one that has the very large concentration of lithium. Spodumene has up to 8% concentration. So how do you build this out? This is a huge sequential planning uncertainty problem, requires lots of analysis, and this is a 5-year project, to say the least. And this will be done in collaboration with the Australian National Science Foundation, which is called CSIRO. So I end up here a little bit also with the human side, and how in our program we're looking at building a community. We had a quite successful symposium in June, attended by 200 people. Was sold out. We had people from car companies like Tesla, as well as the major mining companies, Rio Tinto, BHP, as well as battery manufacturing companies, but then also people from areas affected by mining, such as areas in Zambia and in the Salton Sea area, which is in California, where Lithium Americas and other companies are looking to use geothermal brines to extract lithium. And so this was also the launch of our industrial affiliates program, which is it's an industrial affiliates program where we collaborate with companies. We have now 6-7 members. Some members are investment companies, others are mining companies, others are service companies, and so this is open to everybody. And we are looking at environmental justice concerns. We have also, I'll be traveling to Africa later this year and look at education. We also have students of mine that are involved in Zambia and in Arctic, but also in mining in the rainforest. In Brazil and Indonesia, these are big issues. And mining is important, but it also has a bad name. And I think one thing that people don't quite understand well is that not all mining is the same. So on the left-hand side is the high-grade nickel deposit I was talking about in Canada, and you can see the mine, right? There's a couple of buildings, and the reason for that is it's mined underground. With high precision mining, so you build tunnels and things like that where you can follow the ore deposit, right? You can do that underground. When you do open pit mining, and this is often done when you have very low grade deposits, you're making these huge craters in the subsurface, because you can't do targeting, right? It's impossible. And this is the largest open pit gold mine. This is also a very low grade gold mine. Now, we don't need gold. And where does this gold go? I always like to show that to people. This gold that comes out of this mine sits now in a bunker somewhere, right? This is the craziness of mining. So we're trying to find more of the high grade metals that are critical for human survival, not gold. We have 200 years of gold reserves for engineering and technology applications. So we also work on education. We're just coming out with a new book where lots of this mineral exploration and Bayesianism and things are being done, as well as other types of applications. And so that's all what I got, and happy to take any of your questions.
Oh, that's fascinating. Thank you very much. I guess one thing I think we didn't go too deeply into the supply chain model, which I think is extremely challenging. Can you go into kind of the considerations you have? Do you have to worry about the demand for lithium across the world, the various applications of lithium, and where those users are, the refining facilities? How deep does it have to go?
I think we want to do that bottom up. We don't want to do any sort of gross economic analysis of 2 billion vehicles and so much lithium. We really want to build this from the ground up. That means indeed that we need to do what is called material flow analysis, which is the analysis of how lithium makes itself into different materials. And the two materials right now is electrical vehicles and glass, and so ceramics. But of course, electrical vehicles is going to dominate. And then this question is, where's the demand going to go? The question is, where are the processing facilities going to happen? And then also, what are the effects of improving and the efficiencies on the processing, and what effect does that have? Where are we going to build the ports? We also thinking of doing this for nickel, because nickel is in a way a little bit more interesting, because most nickel comes out of Indonesia and Brazil in the rainforest. And so there's talk about, well, Indonesia wants to decarbonize because they have a lot of coal, and how we're going to pay for that. Well, some people say, let's do more nickel mining in Indonesia, but that's, is that a good idea? Because if you do more nickel mining in Indonesia, that may disencourage people to do high-grade nickel mining in Canada. So there's a lot of this feedback, balancing and reinforcing. And that's where we're going to use this kind of system dynamics, really talk to economists and say, what are you expecting when we do this and this kind of incentives? And so the idea of the intelligent design of the supply chain is to really run scenarios, but do it really from the ground up. I mean, looking at specific resources, right? Looking at, say, how much is there still in Australia? What is Australia doing in terms of its reserves? What is America doing in terms of its reserve? When do we see that coming online? When should it come online? Where would you put the processing plants? And how much investment would that take? And for lithium, this is very fascinating, because, there are now car companies or end users like Mitsubishi. They want to ally with Cobalt Metals to go mine in Canada, right? It's people want to buy parts of mining companies, so it's a very dynamic environment.
So that makes a lot of sense. And is your use case? I mean, I'm hearing two. One is more like a national lab says, here's the possible outcomes for the world. Here's a few studies, or maybe a tool that you can run your own simulations, or working with a conglomerate to actually execute a plan.
No, we're not interested in scientific analysis. We're interested in platform for conglomerates to run these, because we have now companies like Rio Tinto in our consortium, and so we're hoping to attract more other types of companies. In particular, we have an investment company now, and so in next week I'm talking to Tesla. So that's a sign where we're aiming quite big with this.
Okay, that makes a lot of sense. Yeah, well, thank you very much. This is fascinating.
Yeah, thank you.